Hello, welcome to this lesson of the Linear Algebra Tutor. Here we're going to tie it all together. I've hinted over and over again that the concept, or the way that I taught you to find determinant of 3 by 3 matrices by just going through that first row and doing it that way, and the cross product of the vectors, I told you that was a subset of a broader thing. And here I'm going to tie all that together for you. In the last section, we have done the cofactors of the matrix. That's really 90% of the work that's required in order to understand how to find the determinant. The bottom line is, I'll state it over again, is that in the previous time when I was telling you how to calculate it, I was having you go through the first row, and then you were multiplying and you had the submatrices and all of that. So I said that we were expanding that determinant about the first row. It turns out that you can find the determinant by expanding through the first row, or through the second row, or through the third row. In fact, you can also go through the columns. You can find the determinant by expanding through the columns. It doesn't matter what row or column you choose. You're always going to get the same answer. For a given matrix, there's only one determinant. There's no way that you can have different determinants. If you accidentally calculate a determinant with a different value, then you've done something majorly wrong, like a computational error or something, because any matrix should always have the same determinant as an answer. So because you can expand through any row or any column for any matrix and you're always going to get the same answer, what I do is I just always expand through the first row, and that's the way I remember to do it when I'm taking a physics course or solving an engineering problem or whatever. But in this class, your professor's probably going to ask you, find the determinant by expanding through the fourth row, or find the determinant by expanding through the second column. So you need to know how to do that. So let's write that down. You should by this time know how to calculate the cofactors. We've done that before. So let's say we're going to expand, it's what is usually called expand the determinant about the ith row. About the ith row, or through the ith row, however you want to write that. And I shudder to write this down because it's not terribly clear, but part of the challenge in linear algebra is for a student to chop through how the book is written and read the symbols and understand what it's trying to tell you. So I'm telling you in layman's terms, so you're just cutting through different rows and columns, but you need to know how to read it. So I'm going to write it down how you might see it in a book. The determinant of some matrix A is typically expanding about the ith row would look something like this. A I1 times the cofactor I1 plus A I2 times cofactor I2 plus dot 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 dot. So I3 cofactor I3 and so on. Now this, if I showed you in a book, most students probably wouldn't understand what that meant at first glance until you really studied it. All this statement is telling you is that you can find the determinant by expanding about any ith row you want, either row number 1, row number 2, row number 3, if you have a really large matrix, row number 5 or whatever. And the way you do it is you take the element of the matrix at whatever row you're at. So that's I is a dummy variable. So if I'm expanding through the first row, I would be 1. So this is the first row, position 1. So I'm taking this guy and I'm multiplying by the cofactor. And then I'm taking in the same row, because I is the same everywhere, in the same row the next element over times that cofactor, and then the next element over times that cofactor. This is exactly what we were always doing when we found determinants of 3 by 3s. You notice I told you to expand through that first row. It's the first element times the cofactor, which is basically the determinant of the submatrix. And then you have the next element times the cofactor there. This cofactor is where the negative sign comes from that I always taught you to insert. And then you have the third element times the third cofactor. All right, so that's how you expand about row number 1. But if you were to expand through row number 2, then you would just be doing row number 2, element 1 times its cofactor, element 2 times its cofactor, and so on. But the cofactors are going to contain the signs. So let me go and write down how we would, that's how you expand through a row. How do you think it would happen if you expand the determinant about, or through, the jth column? We're going to use a different letter so that we don't confuse it with what you've written up above here. Well, it's going to be the exact same equation. Very similar. So we can say the determinant of A can also be written as A1J C1J plus A2J C2J plus dot dot dot. Again, if you read this in a book and you don't know what it says, you might stare at that for a while and not know what the heck it means. J just locks down whatever column. So let's say you want to expand through column number 1. So then J just becomes a 1 everywhere. So then what you do is you take the element 1, 1 times the cofactor at that location. That would be the element up in the upper left, plus the element on the second row, first column, so that's coming down through that column, coming down, this element times its cofactor, and then you go down again all the way until you go through the matrix through whatever column you're expanding. Of course, you can go through column 1, column 2, column 3. Now, the negative positive is just going to come out from the cofactor expansion because we've talked about that in the last section. That's how it happens. And to remind you of that, I will draw a friendly little picture of the pattern of cofactor signs. It's plus, minus, plus, minus, minus, plus, minus, plus, plus, minus, plus, minus, minus, plus, minus, plus. Nice pattern, right? And it just keeps going on and on forever. You're typically not going to have a matrix larger than 4 by 4. I mean, it just gets cumbersome. And in real life, you don't really have to deal with matrices much bigger than that anyway, because most real systems aren't going to have that many simultaneous variables. I'm not saying you're never going to find one, but it's unlikely. All right, so let's flex our muscles a little bit and actually do this. Let's go ahead and put the same matrix up on the board. Matrix A. This is the one we've been working with for quite a while. Negative 1, 1, 2, 0, 6, 3, 4, 7, 5. And what we want to do is we want to expand about first row. And we're going to get the answer, and then after that we're going to expand through a different row, and I'm going to show you that you get the same answer either way. So the determinant of A is going to be what? Well, it's going to be, to write it in terms of cofactors and stuff, just since we're learning it, we're going to expand through the first row. So what we're going to have is A11 times the cofactor at that location, that's up here, plus A12, C12, this is row 1, column 2, that's this guy, times its cofactor, plus A13, C13. So basically, to expand through a row, you take the element times its cofactor. You take this element times its cofactor. You take this element times this cofactor. This is how you expand through row number 1. All right, so let's go ahead and do that. What you're going to have is A11 is negative 1. And then what do you have for the cofactor? Well, you know from experience that it's going to be a plus because you're going through the first row. So this is going to be a plus, and then it's going to be times the determinant of the submatrix formed when you do this. So 6, 3, 7, 5. This negative 1 is coming from the coefficient, but it's a positive cofactor, so I don't have to do anything else here. Then here I'm going to have, just to make it totally formal, plus A12 is going to give me a 1. That's the coefficient here. The cofactor here, we know from the second position, is always negative. This is why I was always telling you, oh, you have to remember to stick that negative 1 in there. That's where it comes from, times the determinant of here. If I cross this and this out, I'll have 0, 3, 4, 5. 0, 3, 4, 5. All right? And then A13, which is the third guy in that row, is going to be 2. And then it's going to be, again, times the determinant of what we have left. We cross it out, 0, 6, 4, 7. And notice there's no negative sign here, again, because the cofactor pattern gives us this. Now, I know we've done this so many times. You may be a little bored of it, but you have to learn how to do this, so we're going to do it. We have negative 1. In here, we do a crisscross. So we have 30 minus 7 times 3 is 21. This gives us a negative, so we'll just stick that there. And then this determinant is 0 minus 12. And then we have a 2, and inside here we have 0 minus 24. All right, so what we have here is negative. This gives us a 9. This gives us positive 12. This gives us a negative 48. So I have a negative 48 right here. So we have negative 9 plus 12 minus 48. The determinant of this matrix is then negative 45. That's the determinant of the matrix, negative 45. This is actually expanding it the same way I've always taught you to expand it. Go through the first row. All right, so let's keep that in our back pocket. Let's move over here, and let's do it a couple more times because I want to prove it to you. I want to, number 1, prove it to you that it's true. Number 2, give you practice. So the same matrix, we're not going to change anything. Negative 1, 1, 2, 0, 6, 3, 4, 7, 5. Let me move the 6 over so nobody gets confused. That's the matrix. Now we want to expand about second row. In other words, find the determinant by looking at the second row. All right, so the determinant is equal to, let's first write it out formally. We will say A21 times the cofactor 2, 1 plus A22 times cofactor 2, 2 plus A23 C2, 3. This is this element here, this element here, this element here, each times their cofactor. That's how you calculate the determinant. You go through the second row just like that. A21 is going to give you, this is expanding through the second row, so it's the coefficient times the cofactor. So if you don't remember, you can always go back to your pattern here and see that on the second row, the pattern starts negative, positive, negative, positive. Okay? All right, you can also see that because this is, when you add these I plus j, you get an odd number, so that's going to make -1 to that power negative. So you have to have a -1 there, times the determinant, and then we have to figure out what the matrix looks like when we go through this column and through, or through this row and through this column, 1, 2, 7, 5. All right, then plus the next guy over is 6, and since this one was negative, this one would be positive, and it's times the determinant. Here we go cut through that row, cut through that column, we get -1, 2, 4, 5. -1, 2, 4, and 5. All right? And then finally we go to the third one here, 3, but notice that this cofactor was negative, this cofactor was positive, so we're back to negative again, times the determinant. We cover this guy up, and we cover this guy up. We have -1, 1, 4, 7. -1, 1, 4, 7. So now we go and realize that there's a 0 here in front of this whole calculation, so it kind of wipes it out. We just stick a 0 there. Then we have the 6, and inside of this determinant we have a -5 minus 8. -5 minus 4 times 2 would give us 8. And then we have a -3 here on the outside, and on the inside we have -7 minus this direction, giving us 4. So we have is a 6 on the inside here. We have -13, and then minus the 3, and then here we have -11. So we're getting a little bit closer. Here what we have is -78, and here we have +33. So when we have -78 plus 33, you get -45. Notice that's exactly the same thing we calculated before. So there's no difference. Exactly the same thing we calculated before. And basically what's going to happen is you're going to get exactly the same answer no matter what row you go through. Now let me go ahead and do one where we go through a column just to show you that it's no real different. So no real difference. Let's say the matrix, we're just going to do exactly the same thing again. -1, 1, 2, 0, 6, 3, 4, 7, and 5. Okay, so what we want to do is expand. Let's go through column 3. Let's make it a little bit interesting. We'll go through that one over on this column here. So we want to go this, this, and this. So the determinant, just to write it out, is going to be A13 C13 plus A23 C23 plus A33 C33. So it's this element times its cofactor plus this element times its cofactor plus this element also times its cofactor. And now we didn't need to find all those things. So this is just going to be the 2. And then you can use the I plus j. We know that it's 1 plus 3, that's 4, so this should be positive for this cofactor. If you forget, you can go look over here. This is a 3 by 3 matrix, so over here this is this column we're going through, so it starts at positive. So this is positive times the determinant of the matrix that's formed. Since we're looking at this, we cover this, 0, 6, 4, 7. Right? Then we go down to 3 times its cofactor. We know this one's going to be negative because this one was positive. The determinant formed here, you cover this, you get -1, 1, 4, 7. Plus, then we have the final guy here. We know that that cofactor is going to be positive. So we say times the determinant of, we cover this, -1, 1, 0, 6. -1, 1, 0, 6. Like that. I know this gets a little old after a while because we're doing the same thing over and over again, but I'm just trying to show you. Inside here, you get 0 minus 6 times 4 is 24. All right, and then over here, you have negative 3. And inside here, you have negative 7 minus 4, crisscross like that, plus the 5. Here you have negative 6, and then you have minus 0 going this way. So we found the determinants. Here we get, this is negative 24, so that's negative 48. Okay. Here, this is going to give you negative 11. Inside here, negative 11 times positive 3 is positive 33. And then inside here, negative times positive is negative. 5 times 6 is 30. So we have negative 48 plus 33 minus 30. And when you do that, you're going to get negative 45. So the bottom line is, no matter how you expand your determinant, whether you go through rows or columns or whatever, you're doing exactly the same thing in all of these cases. You're just taking the element times its cofactor plus the next element times its cofactor plus the next element times its cofactor. And exactly the same thing is going to happen if you have larger matrices in this. If you have a larger matrices than this, like if you were doing a 4 by 4, you would be going through the entire row and you would have 4 elements, you know, times each of their cofactors. But when you have larger and larger matrices, see, sometimes these 2 by 2s are not quite so easy. They might become 3 by 3s. Like if you had a larger matrix here, when you cross it out and to find the cofactor, then what you're left with is a 3 by 3 matrix to find the determinant. So you have even more work to do to evaluate these little determinants everywhere if your original matrix is much larger. So because of that, typically, I can't guarantee anything, but typically on a test, your teacher will probably stick to 3 by 3 matrices unless they're just mean. Then they will give you a larger ones. But the exact same math holds true for all of them. You can find a matrix by determinant of a matrix by expanding through any row or any column. However, outside of this class, when I'm actually doing it, I always expand through the first row, as I've told you many times before. So make sure you understand this. Determinants are used a lot. They're used even in differential equations and other math classes. They're used, as we've seen, cross product of 2 vectors, a determinant pops up. They're used a lot. They're also used you can solve systems of equations using something called Cramer's rule, which is basically just taking a bunch of determinants of your system. I've covered Cramer's rule extensively in my matrix algebra tutor, so if you want to review that, you can go review it off in the matrix algebra tutor. Basically, all you do is you take determinants and you start dividing them to solve your system of equations. So make sure you understand this. We're going to switch gears a little bit in the next section and kind of build upon this, but ultimately we've now learned how to calculate determinants using several different ways. So make sure you understand them, make sure you're fluent, and then follow me on to the next section to continue with linear algebra.